atmosphere. Okay? Now this is actually another area where we were led to a false conclusion by a simple observation, which is the temperature of the top of the clouds. When we look at Venus, we're only seeing the top of the clouds because the planet's completely shrouded. We can deduce the temperature of the top of the clouds by looking at infrared radiation reflected off the clouds. And what we get is about 240 kelvins. Not that different from the temperature at the cloud tops on Earth. So, scientists concluded based on this that if the cloud top temperatures are similar, then probably it's similar all the way down to the planet's surface. And if it's tempered like the Earth, there could even be flowing water, there could even be life on Venus. And it was known that there's a lot of carbon dioxide in the clouds, but there's no problem with that because we know carbon dioxide is associated with plant life. So it was thought for quite a long time that the surface temperature on Venus was probably just a little higher than Earth's surface temperature. And this was again thrown into complete mayhem by the fact that the surface could be observed using radio astronomy again in the 1960s. So you can see how radio astronomy in the 1960s completely revolutionized our understanding of Venus, everything about Venus and Mercury. All right, so what's happening in this technique is a little different than what we talked about a moment ago with the rotational broadening. Because in this case, we're not sending out a radio signal and then looking at redshifting, blue shifting, and all that because of spin. Instead, we're just passively observing Venus with a radio telescope, which is a big dish, basically. It's a big radio antenna. And we're observing radio waves from Venus, but they're radio waves that are actually naturally generated on Venus, on its surface. And if we do that, we can make a plot of brightness like we like to do. And you get this curve, typical black body type shape where there's a peak at some wavelength. And we can actually apply Venus law, just like we talked about doing before. And when you do that, you get a surface temperature of 600 kelvins. So incredibly not like the Earth. Actually quite similar to the surface temperature on Mercury. So this was pretty surprising and completely squelched any notion of any life on Venus as we know it, right? Because at those temperatures, molecules basically fall apart. Especially biological molecules are pretty frail. DNA is not going to survive at that temperature. The surface of Venus has been explored by quite a few spacecraft. We have even more spacecraft have explored it in orbital form. European, American, Soviet spacecraft. Only the Soviets actually landed on Venus and were able to actually pull that off. And it's kind of a fitting Soviet thing to do. Survive the turmoil of actually making it down through that atmosphere and get to the surface and take photographs. It's quintessentially Soviet kind of accomplishment. But they didn't last very long. The nearer spacecraft, as they were called, were crushed by very high pressures, and they're all corroded away now because not only is it very hot on Venus, but it actually turns out to be a highly corrosive and even acidic atmosphere. I mean, it makes what we call acid rain on Earth seem like a blast of Alka-Seltzer or something. We're talking about an atmosphere that's actually got clouds that are primarily composed of sulfuric acid, condensed sulfuric acid. So imagine a cloud of sulfuric acid. I mean, it's a pretty nasty place. The air, what passes for air there, is actually mostly carbon dioxide. Now, if we look by comparison at the Earth, and compare Venus with the Earth, we see carbon dioxide on Venus is about 96% of the atmosphere. It's only about 0.4% on Earth. Now, if you remember what everybody's talking about these days is the greenhouse effect and global warming and all that, right? Well, here we've got an atmosphere that's 96.5% carbon dioxide. Now, actually, that by itself doesn't really tell you anything because you kind of have to know how dense the atmosphere is because it could be almost a vacuum and still be 96.5% carbon dioxide. Okay? But actually, it's about 10,000 times more dense than Earth's atmosphere. So it's an incredibly dense atmosphere that's mostly carbon dioxide. So just as your imagination is probably running wild thinking about this right now, there's an amazingly strong greenhouse effect on Venus, and that's tied with this high temperature. So it's kind of like a greenhouse effect, you know, on steroids here. It's the sort of that could indicate the trend on Earth if we do continue to add carbon dioxide to our atmosphere. we'll probably never get to the point where it's that hot. I mean, we don't have to get anywhere near that point before life is going to be extinct on the Earth anyway. But this just goes to show you how significant carbon dioxide can be. There's no water, practically no water. There's really no free oxygen. And so we have an atmosphere that's totally unlike Earth's atmosphere. But we believe that the planets actually started out with the same materials. Now, they have the same mass and the same radius. They started with the same materials. So somehow the evolutionary paths of these two planets are radically different from each other, and it's got to be tied to the distance from the sun. That's the only major difference. Venus is about 70% of the Earth's distance from the sun. All right, so we'll talk about that. But first, as usual, we look at a plot of temperature in the atmosphere of the planet that we're talking about. And what we see here is a typical curve. We're going to see this curve over and over again. There is a difference, though, compared to the Earth, because remember the Earth has a bump in the temperature in the ozone layer. Venus just has a dip there, and then it starts to have a higher temperature as you go out into space and get exposed to solar radiation. But look at the numbers here at the surface. The zero altitude at the bottom of the plot, you read over to about 750 kelvins. So the temperature on Earth would have only been about 300 kelvins. So this curve is about twice as high, basically, as the temperature that we would see on the Earth. And we also can read the pressure, because the pressure scale is on the right side. And remember, when we get to the surface of Earth, we would have 1 bar, because a bar is surface pressure on the Earth. So at the Earth, this curve would have a 1 down here, but it's got 90 instead for Venus. So Venus's atmosphere is 90 times the density and pressure of Earth's atmosphere. And on top of that, again, it's got this sulfuric acid cloud layer. So incredibly hot, incredibly high pressure, and acidic. This is one of the first shots from the Venera spacecraft. This was the early black and white Venera version, and this is kind of part of the lander zone foot pad right there. And you look out, and it looks sort of like you landed in the bed of one of those paving trucks that scrapes up the pavement on 95. They're repaved, these big chunks of asphalt. It kind of looks like that. It's very carbonaceous material. In fact, it's material that might even sluggishly flow due to the high temperatures. And then we have later missions that have higher resolution photography. All these landers were, of course, long fried by the fact that we're sitting in this very, very difficult atmosphere. You can see now. There may actually be some evidence, nonetheless, for life, as we'll see. Another shot. Coming up here, the first colored Venera. First colored Venera there. You can see Venera TV, and you can actually see that it's not only dark stuff, but we actually also see sulfurous-looking rocks. And as I mentioned, evidence for possible life turns out not to be true. It's one of those things. We have to use the scientific method and actually reject that as evidence for possible life. But it was there. I thought we saw it a moment there. But actually, there is one way in which that makes sense, because, of course, it has the right color to blend into the surroundings, right? Could be an evolutionary adaptation of the yellow. Just saying, not really a reduction of Venus, but anyway. So again, evidence for this very sulfur-rich atmosphere, as well as very highly carbonaceous rocks. Okay, so before we end today, I just want to quickly just flesh out this idea I was just talking about. We've got the combination of high carbon dioxide composition in the atmosphere, as well as its very high temperature. So we think that they really are coupled together by this idea of a greenhouse effect. So whereas on Earth, we have what we call a greenhouse effect. It's a mild effect on Earth. It's actually a good thing to have a certain amount of greenhouse effect because it moderates temperatures. It protects us from the wild temperature extremes that you see on the moon, for instance, right? The moon, you're going from 100 Kelvin to 400 Kelvin every day. On the Earth, there's only about a 20 or 30 Kelvin variation. And that's partly because of the thermal blanket that we have in the atmosphere. So a little CO2 creates a little greenhouse effect. That's a good thing. But what we think happened on Venus is that when the CO2 and H2O were outgassed from volcanoes during the early period on the planet, to form a secondary atmosphere, we actually had a situation where it was too hot for precipitation to occur. Now, in the case of the Earth, precipitation occurred, and actually we were able to take some of the carbon dioxide, and it was actually dissolved into oceans. But because the temperature was so high, the atmospheric water vapor remained as vapor, did not condense. We didn't have the biblical floods and the oceans forming, and so the carbon dioxide never actually was able to form into carbonaceous rocks or into any of the carbonaceous compounds we see in the ocean beds on Earth. So instead, we have this very heavy blanket of greenhouse gases. And what happens is the temperature goes higher and higher on Venus because we have a buildup of heat. In fact, the temperature historically may have even been as high as 1,500 kelvins. That's about twice as high as what we see even now. And if you think about what happens to an atmosphere when it gets hot, remember that we're going to lose more and more particles, right? Just like we keep talking about. You have higher temperatures, you have higher thermal velocities, you lose material into space because it exceeds the escape velocity. Well, this was particularly insidious in the way it affected the water that was present on Venus. There probably was water there originally. But what happened was, we think, that as the atmosphere puffed up due to the very high temperatures, the water vapor reached such a high altitude in the atmosphere that it was broken up by solar ultraviolet radiation into hydrogen and oxygen. Remember, hydrogen is the lightest gas. It only has one proton in the nucleus. Very low atomic weight. So at a given temperature, hydrogen is going to zip around in velocity much faster than any other atom. And so what that basically means is the hydrogen is going to immediately evaporate into space. So the hydrogen velocity, oxygen remains, but it reacts with other compounds. And what we end up with is a lot of carbon dioxide, no water. And now, because Venus is a very dry planet with no water, you can never form oceans and pull that carbon dioxide out of the atmosphere. So that's what we call a runaway greenhouse effect. It's completely out of control. It's gone off the scale. And now there's even been chemical change because the water's just gone. It's not just sort of frozen underground like we think for Mars or polar ice caps or something like that. It's actually gone because it was destroyed by solar radiation. So this is an irreversible process. And we think, therefore, that Venus is in this permanent state of a very high temperature now. Okay, so I guess we'll finish going through this on Thursday. Remember, go out and vote.